All right, folks, we are back with some more examples. This time we're going to look at some Chapter 17 examples. And a lot of these you can find in the textbook, but sometimes it's helpful to actually see them explained. So we're going to go with that kind of theory here. So we're going to start here with identifying the acids and bases in these reactions and the corresponding conjugates that we find. So let me bring this back to the whiteboard. So let's start here with our first reaction, okay? Now we want to look at a few things before we even start this problem. I know it might seem like a basic overview, but it's good to remind ourselves of some of the terminology that was used in the question itself. It asked us to identify the Bronsted-Lowry acid and the Bronsted-Lowry base. Okay, so knowing the definition of these two things would be critical just right off the bat, right? So we're talking about the definition of a Bronsted-Lowry acid. We're talking about something that's a proton donor. And a Bronsted-Lowry base would be the opposite then, a proton acceptor. All right, now this word right here is going to be the important one when we're talking about the difference between an acid and its conjugate base and a base and its conjugate acid, because I want you to notice something. All right, so let's erase these definitions. Now, when we're looking at the reaction itself to try to decide, is it acid or base? Is it, where are the conjugates, things like that. It might be a good idea, first of all, to look at what this word means, right? And at least in the way that we're using it here. One of the definitions for the word conjugate are things that are related to one another, things that are connected or related to one another. So when we're looking at conjugate pairs, they're going to be the components in your reaction that are almost the same substance, okay? What the conjugate pairs are going to differ by is going to be a proton. Okay, so if we keep that idea in our mind that we're looking for the difference of one proton between the two parts of the pair, we can see, for example, in the water molecule here, right, it's H2O. On the other side, we have H3O plus. The difference between H2O and H3O plus is the addition of this proton, right? Over here, the difference between H2SO4 and HSO4 minus, well, the HSO4 minus looks like it lost one proton. All right, so that's how we're going to find the things that make up our pairs. Now, in terms of labeling, which is which, on your reactant side of the reaction, you're going to have one acid and one base. Okay, and you're going to decide which is the acid and which is the base based on which component is accepting a proton and which one is donating a proton. Okay, on the product side, that's where you're going to have one conjugate acid and one conjugate base. Okay, and the relationship here is that whatever your base was on the reactant side, it's going to have a conjugate acid on the product side. And whatever your acid is, it's going to have a conjugate base on the product side. Okay, So when we're looking at our two reactants here, we see that for our H2SO4, it went from H2SO4 to H1SO4 minus. So in this case, H2SO4 is our proton donor. H2O went to H3O plus. So water is our proton acceptor. Okay, based on that Bronsted-Lowry definition that we looked at just a few minutes ago, that makes the H2SO4 our acid, and it makes the water our base. Okay, but if we follow these lines, that means that our HSO4 minus will be our conjugate base, and our H3O plus will be our conjugate acid. Okay, so that's how this setup works. We're going to look at 3 more examples, but I'm going to rewrite them on the board. All right, so I just paused to write all these reactions out so you didn't have to watch me do that. But now we can go through them one at a time. And so when we're looking at these, we're going to be looking at first, I like to find the pairs before I start. So that's how that's always my first step. So I like to find the things that are related. So right away I see that HCO3 minus and H2CO3. Those are going to be that's going to be my first pair. They differ by a proton, and that's what you're looking for. H2O and OH minus also just differ by 1 proton. So that'll be my second pair. In this case, my HCO3 minus accepted a proton and became H2CO3. All right. So in this case, the HCO3 is going to be the base, and the H2CO3 is going to be the conjugate acid. H2O, on the other hand, it donated its proton. It was a proton donor this time, so it's going to be an acid in this example. And the OH minus will be its conjugate base. It's one of the special properties that water has, that it's able to act as either an acid or a base depending on the solution that it's in. Okay, so we saw in the previous example where water was acting as a base. In this example, it's acting as an acid. Okay, we'll move down to our next example. Even if you see compounds like this one that you might not necessarily be familiar with when you first look at the reaction, you don't have to know what the compound is to understand the process that's happening in there. Okay, like we could see right away that we went from C5H5N to C5H5NH plus, right? So what did we do here? This compound, it accepted a proton, right? Because it's 1 proton, it has 1 additional proton in this form of the compound. And by definition, if it accepts a proton, that means it's a base. We don't have to know anything else about it, but we can see just based on these 2 forms that this compound accepted a proton to become this compound. And if this is your base, that makes this its conjugate acid. All right. If this is the base, even without doing any more thinking about it, once you recognize that this compound is the base, we know that water automatically is going to be the acid. I mean, yeah, we can reason it out still like we did in the last one, but you know, your reactant side can only have a base and an acid, right? When you're looking at these reactions, it's not going to have two bases. So when we have a base over here, we have our acid over here. If water is going to act as the acid, then on the product side, that means that OH minus is going to be its conjugate base. Okay, and then down here, we have HNO3, which is going to convert to NO3 minus. So it donated its proton. That makes HNO3 the acid, which means that water in this case is going to be the base. If HNO3 is the acid, that makes NO3 minus our conjugate base. Okay. And if H2O is our base, that makes H3O plus our conjugate acid. Okay. So when you have a base and you want to find its conjugate acid, all you do is add a proton. When you have an acid and you want to find something's conjugate base, all you do is remove a proton. So that's the relationship there. So now we're going to look at some calculations involving KW. Erase this board. So we're going to calculate the hydroxide ion concentration for everything listed here at 25 degrees Celsius for each solution, and then determine if the solution is acidic, basic, or neutral based on those concentrations. Sounds easy enough, right? I know you're all excited. All right, so for part A, we're starting with a concentration of H3O plus of 7.5 times 10 to the negative 5 molar. Okay, now what they're asking us to kind of exploit here is this relationship between our KW value and our hydroxide and hydronium ion concentration. Okay, so we're going to see that relationship written like this. Our KW equals H3O plus times OH minus. And this is going to equal 1 times 10 to the negative 14. Okay, because that's the value of KW. Just to be clear though, you may also see it written like this. Right, and this means the same thing. Okay, this is your hydronium ion, and this is your hydrogen ion. But these two things are used in just interchangeably throughout your acid and base chapters to represent the acidic kind of component of a solution. Okay, so I might switch back and forth between them. Your textbook might, Professor Sheehan might. Just don't be surprised when we use either term to represent that acidic part of the solution. In either case, though, what we're really going to focus in on is how to use this KW expression to solve for our hydroxide ion component. Okay, now we can pretty much set this up like just like a math problem at this point, right? Because this is our unknown, so we can solve this expression for hydroxide. So to find OH minus, it's going to be KW divided by H3O plus, right? Because I'm going to divide H3O plus over here. I'm going to divide H3O plus over here. And then I get my new formula. All right, now I'm just going to plug in the values that I know. So let's take that away. So I know the KW value, that's a constant at 25 degrees Celsius. It's always going to be 1 times 10 to the negative 14. And I'm going to divide it by my H3O plus concentration, which they gave us in the problem. Okay, and 1.75, that's going to be 1.3 times 10 to the negative 10 molar OH minus. Okay, so that's our concentration of OH minus. And the next part of the question asks us to determine whether the solutions are acidic, basic, or neutral. And we can look at the relationship between the hydrogen ions and the hydroxide ions to figure this out. Okay, let's make ourselves like a little reference down here. Okay, so we're going to start, we'll have neutral, and then we'll have acidic, and we'll have basic. Okay. Now, when you're neutral, you're going to be at a concentration of your hydrogen ions or your hydroxide ions of 1 times 10 to the negative 7. Okay, that's your neutral level. All right, let's actually switch this out because we're not talking about the pH scale here. We're talking about concentration levels. So this is going to make more sense if we orient it this way. So when you have concentration values of your hydrogen ion that are larger than neutral, okay, of hydrogen ions. So when your H plus is greater than 1 times 10 to the negative 7, that's going to be an acidic solution. When your H plus is less than this value, smaller than this value, it's going to be a basic solution. Okay, that's in terms of your hydrogen ion. Okay, we can also look at this in terms of your hydroxide ion though, because we have both of them present for us here, right? We can look at our hydrogen ion and our hydroxide ion, but I want you to really look at both of the components and numerically what, I don't know, kind of like what the concentration is and how it's then represented in terms of the acidity or basicity. So if we look at our hydroxide ion concentrations, we're going to see like the reverse relationship here. So when my hydroxide ion concentration is greater than 1 times 10, that means I have a basic solution as well. But if my hydroxide ion concentration is greater than 1 times 10 to the negative 7, then kind of automatically my hydrogen ion concentration is going to be less than that. Because when I multiply these two things together, I still have to get my Kw value back out. So the concentration of one thing, is going to be like dependent on the concentration of the other. So this like opposite relationship here should make sense. And then if we go back over onto the acidic side, if my hydroxide ion concentration is less than 1 times 10 to the negative 7, that also indicates that I have an acidic solution because it means I have more hydroxide ion than more hydrogen ion rather than hydroxide ion. Okay. So if I have more hydroxide ion, my solution is basic. If I have more hydrogen ion, my solution is acidic. That's how I'm going to determine whether something is acidic or basic based on these values. So when I look back up at the two values that I have here, I have my hydrogen ion value 7.5 times 10 to the negative 5 versus my hydroxide of 1.3 times 10 to the negative 10. I see that this value is larger. And if my hydrogen ion value is larger, that means the solution is acidic. Okay. So if we look at our next calculation, we have H3O plus is going to equal 1.5 times 10 to the negative 9. Okay, and we know that Kw is going to equal H plus times OH minus. So again, if we solve out, we're going to solve out and isolate that hydroxide ion, and that's going to give us the formula that we use. So to find OH minus, we'll take our Kw and divide it by our hydrogen ion concentration. Okay, so I'll write it over here. So our hydroxide ion concentration then is going to be 6.7 times 10 to the negative 6 molar. Okay, so there's my hydroxide. There's my hydrogen ion concentration. I see here that my hydroxide ion concentration is larger than my hydrogen ion concentration. So this solution is going to be basic. Okay. And the last calculation, I think they're just throwing this in here for like a demonstration. Because they give us a hydrogen ion concentration of 1 times 10 to the negative 7. And we should know right away that that's our neutral value. We can solve for it though and just like see for ourselves that our OH minus concentration is going to be the same number. Right, so we'll take their Kw, divide it by 1.0 times 10 to the negative 7. And what we're going to get back out is 1 times 10 to the negative 7. Okay, so when your hydrogen ion concentration equals your hydroxide ion concentration, that means that you have a neutral solution. All right. So now we're going to look at a couple more, but we'll solve for our hydrogen ion concentrations instead. So just take a look at those problems. I'll erase the board. And we're going to go through the same process for these. Okay. So instead of having hydrogen ion concentrations this time, we're given hydroxide ion concentrations, but we're going to solve for our missing variable the same way. Okay, but this time we'll divide both sides by our OH minus. And that's going to give us our hydrogen ion concentration. Okay, so this will be the formula that we can use to solve all of these. Okay, so we know that our Kw is 1 times 10 to the negative 14. In this case, our hydroxide ion concentration is 1.5 times 10 to the negative 2. Okay, so our hydrogen ion concentration here is going to be 6.7 times 10 to the negative 13. Okay, so when we compare our hydroxide ion concentration to our hydrogen ion concentration, we see here that the hydroxide ion concentration is larger, so solution A is going to be basic. All right. For problem B, we see that the OH minus concentration is 1 times 10 to the negative 7. So I'm not even going to calculate that out because we should know right away that that's going to be neutral. Okay, and then for our last one, can set up our calculation. Okay, and we get 1.2 times 10 to the negative 5 molar here. Okay, so when we compare our hydroxide ion concentration to our hydrogen ion concentration, we see that this one is larger. Our hydrogen ion concentration is larger, and that makes the solution acidic. All right, so hopefully that seems pretty straightforward. Now we're going to do some pH calculations, which are fun. All right. Let's pause and let me erase this whiteboard real quick and write down some of these numbers. Okay, so I had a chance to write down these problems up here. So we're going to go through and we're going to calculate the pH of each of these solutions. Okay, and then we'll figure out from the pH whether the solution is acidic or basic. You can actually tell whether the solution is acidic or basic based on these concentration levels that they already provided for us here. If we go back to the method that we used in the last problem, we can look at the level of hydroxide ion concentration, for example, and figure out whether it's acidic or basic without calculating the pH. But we want some practice at that anyway, and then we can talk a little bit about the pH scale. And I want to talk about a few other calculations that are related to this as well anyway. Okay. So our pH scale, it's one of these logarithmic scales, and it's going to be related directly to the amount of hydrogen ion that you have in your solution. Okay, we're encountering quite a few of these P scales in this chapter. Okay, and each of your P scales is going to be related to the notation that follows the P, basically. So your pH scale is going to be related to your hydrogen ion concentration. Your POH scale is going to be related to your hydroxide ion concentration. Your pKa scale is going to be related to your Ka value. And your pKb scale is going to be related to your Kb value. All right. And you're going to calculate these P values, I guess, we can call them, the same way. All right. We're going to take the negative log of whatever this thing is that they're indicating. So to find the pH, it's going to be the negative log of our hydrogen ion concentration. If we wanted to find the POH, it's going to be the negative log of our hydroxide ion concentration. To find our pKa, it should be, it gets repetitive at some point, but it's all right. It's going to be the negative log of our Ka value. And if we want to find the pKb, that's going to be the negative log of our Kb value. All right. So another interesting thing that we can look at here is the relationship between these two sets. Okay, so I'm going to separate them out. They're kind of paired up, right? That makes sense. So this is one pair and this is another pair. What's interesting here when we look at our pH and our pOH values is that if we took our pH value of, if we calculated the pH value of this solution, okay, and then we also calculated the pOH value of this solution, and we added up the pH and the pOH values, they would add to 14, right? Just like if we, took the H plus concentration and we multiplied it by the OH minus concentration, that would give us Kw, which is 1 times 10 to the negative 14. All right. If we look over here at our pKa and our pKb values, we're going to see the same type of relationship. If we take our pKa plus our pKb, we add them together, we're going to get 14. If we take our Ka value, we multiply it by our Kb value, it's going to give us our Kw value. All right. That means that when we have just one of these values, right, if we just have our hydrogen ion concentration, from that we can find our OH minus concentration if we use Kw. We can also find our pH and our pOH. If we are only given a pKa value, from our pKa value, we can find our pKb. We just have to subtract it from 14. Once we have our pKa or our pKb values, we can find our corresponding Ka and Kb values. All right. Let's just write down the formula actually for that reverse process because I don't, it's not written down over here. We have this formula here where we can find pH by taking the negative log of H plus, but we can also kind of do the reverse process. If we have the pH value, we can find our H plus concentration by doing 10 to the negative pH. Okay, because these are like, we can think about them like opposite processes, right? They're linked, but they're opposite. And that process carries through to all of these things. Okay, if I have a hydroxide ion concentration, or if I have a pOH rather, and I want to find a hydroxide ion concentration, I just need to use my pOH value. So I'll take do 10 to the negative pOH, and that'll give me my OH minus concentration. If I want to find my Ka value, Ka is going to be 10 to the negative pKa. My Kb value is going to be 10 to the negative pKb. Okay, just notice that whatever follows the P in the pKb, that links back to the thing that you're finding. Okay, so you don't want to confuse yourself and like do 10 to the negative pKa and then assume that it's your Kb value. So don't do that. Just understand that these two things are always going to be connected. All right. There was a lot of intro before we got into, but the next few problems are going to use all of this information. So we want to make sure that we're aware of it all. All right, so let's look at these. So we're starting here with a hydrogen ion concentration of 1.8 times 10 to the negative 4 molar, and we want to find our pH. So that's just going to be the negative log of this H3O. Sorry, that should look more like a bracket of our H3O plus concentration. Okay, so it'll be the negative log of 1.8 times 10 to the negative 4. Okay, and we get a pH of 3.74. Interesting thing when you're doing these calculations in terms of your significant figures. However many significant figures you have in your concentration value here, that's how many decimal places you're going to include in your pH. So I have, you know, 2 sig figs there. So I'm including 2 decimal places here. All right. So for our next one, now we can go, I'm going to show you both ways to calculate this. And you can do either way is perfectly fine. All right. The first thing you can do is you can use your relationship with Kw to figure out what your hydrogen ion concentration is from this value. Right, so this is just like what we did in the last problem. All right, once we have this hydrogen ion concentration, now we can find the pH. And we get 12.11. All right, or we could take this concentration and we can find the POH from it right away. To find the POH, we'll take the negative log of our OH minus concentration. And our OH minus concentration is 1.3 times 10 to the negative 2. Okay, and we get a POH value of 1.89. Okay, now I want to find my pH value. I don't want to just leave it as my POH, but we remember that pH plus POH equals 14. So if I want to find my pH value, I can just do 14 minus POH. So 14 minus 1.89. And shockingly, my pH is still going to be 12.11. So either of these methods, we'll put a big or over here. You can do either of these things to calculate the pH in this second scenario. All right, and obviously if we have, we're talking about our pH scale. So this is when we should have our acidic on the left and our neutral here and our basic here. So our pH scale starts at 0, and 0 is going to indicate acidic. And as we move up to the pH of 7, that's when we're at our neutral. And anything above 7 up to 14 is going to be basic. And sometimes you do find pHs that dip a little bit below 0, like you'll be like negative 0.25. That's just something that's very concentrated, very acidic. You also might find something that's basic that's like 14.07, or and you're like, why is it above 14? It happens. There's like a little plus or minus at the end of each of these values. But we can see here that our pH of 3.74 is going to be acidic, and our pH of 12.11 is going to be basic. All right. So let me erase this. Pause this while I erase it, and I'll put up the next ones. Okay, so here we have our second set of calculations. Obviously, example C is a little bit easier because we're already in terms of hydrogen ion concentration here. So we'll take the negative log of that value. All right, we get a pH of 8.02, and that pH value is going to be basic pH because it's above 7. And then over here, again, we have two options. We can solve for our H plus. Okay, so we have a hydrogen ion concentration here of 1.4 times 10 to the negative 12. We can find the pH from that. Get a pH of 11.85. Or we could take the POH, which is the negative log of our OH minus. That's 7.1 times 10 to the negative 3. So our POH value would be 2.15. So to find our pH, it's going to be 14 minus POH, which will be 14 minus 2.15, which is 11.85. Well, either way, we have a solution here that is basic. Okay, so hopefully that makes sense because we're going to build on this in the next problem. Here we're going to do calculations. We're going to do 3 calculations given 1 variable. Okay, and this is that connection I was mentioning before when we were drawing out those formulas, how if you have 1 out of the 4 values, you can find the rest of them. So here we're given pH values and we're asked to find everything about that particular solution. Well, I guess not everything, but you know, the other 3 variables we're asked to find from that pH value. So the first solution has a pH of 4.80, and we're going to build from there. Okay, there's no right or wrong way method-wise to do this. You know, we know the things that we want to find. We want to find POH. We want to find H3O plus. We want to find OH minus. So there are multiple ways to do these things. There's not like one right way, one wrong way. The POH calculation though is pretty easy. So, you know, maybe we start there just to get one of them out of the way. So to find our POH, it's going to be 14 minus the pH. Should be 14 minus 4.80. So our POH value is going to be 9.20. Okay, so we can write that there. Okay, now that we have pH value and a POH value, it's going to be a lot easier to find our concentration values. All right, so I'll box this first calculation off. So to find our hydrogen ion concentration, we're just going to do 10 to the negative pH. Easy as that. So I want to do, I mean, in my TI-30 calculator, I'll do the 4.8, hit the negative sign, and then I'll raise it to the 10. Okay, and again, if we have 2 decimal places in our pH, that means we're going to want 2 significant figures in our concentration. So we're going to round this to 1.6 times 10 to the negative 5 molar. Okay, now from here, to find the hydroxide ion concentration, you can use kW or you can use your POH. Okay, I'd like to get you a little more familiar with using the POH value, so I'm going to use that here. But maybe we'll use the other method in the next problem. So we're going to do, to find our hydroxide ion concentration, we're going to do 10 to the negative POH. We found our POH to be 9.20. And we get a hydroxide ion concentration of 6.3 times 10 to the negative 10. Okay. So see all that information that we can find just from this one piece of information. We were able to find all three of these pieces of information. Okay, so let's do that for the next one as well. In this one, we're starting with the pH of 8.37. That's our first piece of information. I'm going to use a different order to approach this problem just so you can see it from a different perspective. Okay, so right from this pH value, the first thing I'm going to do here is I'm going to find my hydrogen ion concentration. So I'm going to do 10 to the negative pH. All right, and I get a hydrogen ion concentration of 4.3 times 10 to the negative 9 molar. Okay, it's my first piece of information. From here, I'm going to use my KW relationship to find my hydroxide ion concentration. Okay, so that's going to be KW, which is 1 times 10 to the negative 14, divided by my hydrogen ion concentration, which I just found. I get 2.3. I said 3, I wrote down 2, that's good. 2.3 times 10 to the negative 6 molar. Okay, so that's my hydroxide ion concentration. All right, last thing I'm going to do is find the POH. So my POH is going to be the negative log of my OH minus concentration. So it's going to be the negative log of 2.3 times 10 to the negative 6. Okay, so we have POH of 5.63. Okay, so we approach that a little bit differently, but that method is still completely fine. Okay, so you don't have to stay like cemented to one particular way to solve these problems. That's how I want to get at. There are a bunch of different ways you can approach them, and the more you understand the relationship between these these four numbers, these four values, the easier it is for you to move back and forth between them. Okay, so the next thing that we're going to talk about is how we use, or kind of like how we deal with these weak acid solutions. All right, we probably have a few things that we need to talk about before we tackle this problem. This question wants us to find the hydrogen ion concentration and the pH of a 0.1 molar HCN solution. Okay, and they give us the Ka value there. Now, you've heard in lecture that you need to know what your 6 strong acids and your 6 strong bases are, right? There's a reason for this, right? Because you need to be able to kind of identify right off the bat what a strong acid is, so that you realize that everything that's not a strong acid is going to be a weak acid, right? As long as it's an acid of some kind. All weak acids have these Ka values that are associated with them, okay? And I think this is the thing that maybe gets overlooked in the transition from the last chapter we looked at to this one, is that Ka values, they're just another equilibrium constant. Right? And we're going to treat them the same way. Every time we see one of these, Ka values, Kc values, Kp values, Kb values, they're just another type of equilibrium, right? And the notation that comes after the K is telling you the type of equilibrium that we're looking at. And here we're looking at an acidic solution. Okay, and the Ka value that's associated with the weak acid is going to tell you how likely it is for that weak acid to form ions in solution. Okay, so if we look at I'm going to write the 2 acids that were on the last slide. We had HCN and we have hydrofluoric acid. We have HF. Okay, HCN has a Ka of 4.9 times 10 to the negative 10. HF has a Ka of 6.8 times 10 to the negative 4. Okay, and just like with the last chapter when we talked about equilibrium, the larger the K value, the more product forms. Okay, and in the case of something like a weak acid, right? So let's say this HCN, the product that's forming are going to be these ions, right? So the larger the K value, the more ions you're forming. The smaller the K value, the more of your acid kind of stays in its molecular form, right? Because the reactant side of that reaction is going to be favored. Now you're going to notice, that there are no K values associated with your strong acids or your strong bases. Okay, and hopefully that makes sense to you, because when we have a strong acid, so something like HCl, right, 100% of that acid converts into ions. Okay, there is no back and forth like with the weak acids. And because there's no back and forth, there's no K value associated with it. All right, you can assume that when you have a strong acid and it's in solution, 100% of that strong acid is going to dissociate into its ions. All right, but how many ions are formed when a weak acid dissociates? It's related back to its K value, because it's not 100% of the acid is going to separate. Okay, so we have to keep that in mind. It's also important to keep in mind that when we're looking at these Ka values and these Kb values, the formula for them is the same as your equilibrium constant formula from the last chapter, when we have a Ka value and we're trying to set up um, an equation to solve for a missing variable, your Ka is still going to be your products over the reactants raised to the coefficients. It's just gonna, it just happens that the equations or the reactions that we're looking at are these acid reactions with water, okay? So we'll look at this and we can go through exactly what I'm talking about here. We're looking at this HCN solution, okay? And you can assume that all of your weak acid solutions are going to be aqueous, right? They're all going to be reacting with water. And the first thing that you probably want to do for yourself when you're dealing with a weak acid or a weak base solution is you want to take the weak acid or weak base you're looking at and write out its reaction with water, okay? It doesn't, I know that some of you like look at the, you're like, oh man, I don't want to write out another reaction. The correctness of your formulas isn't going to make or break you here, so you shouldn't panic about that. But you have to understand what's being represented in each part of the formula. Okay, so HCN is going to represent your weak acid, and you're going to be reacting it with water, and we'll leave water in its liquid form because the auto ionization constant for water is much smaller than the Ka values, so it's going to be, we'll call it a negligible contribution here. So we could just leave that alone. Okay, we're going to put it in here because these two things react together, and I want to represent it. But we're not going to put anything numerically in our water column. Now, what happens between these two things? Okay, remember, acids are proton donors, so it's going to donate this proton to the water. That means it's going to form H3O+. Okay, and what's going to be left behind? RCN-. Okay. Now, once you have your reaction represented like this, now you can make what hopefully by now you've come to think of as your beloved ice table, right? I know when you first saw the ice tables, you're like, they're terrible, but by now you're probably like, oh, they're the best thing. They're so fun. So I'm gonna X out my water column. I also like to leave my water column there and X it out because it makes a very good dividing line between my reactants and my products. Okay. And we're going to kind of set this up the same way initially, where they gave us an initial amount of our weak acid, and that's 0.1 molar. Okay. And we can assume that initially we don't have any product. That product is going to come as the acid dissociates. Okay. As the weak acid starts to separate, its concentration is going to decrease because it's going to be forming its ions, and we're going to be creating the ions here. And we can represent our equilibrium rho as 0.100 minus x, x, and x. Okay. So now we are going to use our Ka value that we were given, which was 4.9 times 10 to the negative 10. And we're going to set up our Ka expression. Now, this is what I mean when I'm saying like all of your K values are going to follow the same format, because your Ka expression here is going to be products over the reactants, but we're not going to include our liquid water because we don't include solids or pure liquids in our equilibrium expressions. We substitute a 1 in for them, like we went over last chapter. So Here are our products. Divide them by our reactants. See, you could put a 1 there if you want to, but we don't have to. Okay. And now we're going to plug in values for this. So we have x times x, which we can write as x squared, right? Because this is an x value and this is an x value, over 0.100 minus x. And that's going to equal our Ka value, which is 4.9 times 10 to the negative 10. Okay. Now we need to talk about this approximation that we make when we're looking at these weak acids and these weak bases. You know, we talked last time that if we have in the last chapter we mentioned, if we have a very small K value, we can assume that this X value that we're subtracting from our initial amount, that it's so much smaller than the initial amount we're starting with that we can take it out of our calculation. That comes back into play here because a lot of these Ka values and Kb values are tiny numbers. Okay, so you know, it all goes back to remembering what a small k means. A small k means that you're not forming a lot of product. That means that most of your HCN is going to stay in its molecular form and only a little bit of it's going to separate out. So if we actually remove x from our 0.1 value, the amount that we get is still going to be very close to 0.1. And that's why we can take this minus x part and we can take it out of our equation. Okay. Now we have to double check every time we do this to make sure that that approximation is all right to make, because, you know, if the ionization is too large, then we have to solve for the quadratic here. Okay, but we'll check that out in a minute. But if the approximation holds up, then we just saved ourselves a lot of effort because now we don't have to solve the quadratic equation, and anytime we can avoid that is a nice time. Okay, so we're going to set this up and we're going to solve for x. All right, so I'm gonna erase this part and come back over here. So I'm just gonna rewrite this so I can I want to, you know, like show all the steps and all that. Okay, so I'm going to multiply both sides by 0.100. Okay. And take the square root of this. Okay. And, you know, remember that these x values that you're solving for, they're these values here. Okay. Now we want to check this out. We're going to do our 5% check. So I'm going to come back over here and we're going to do our 5% check. Okay. So you're going to do your x value and you're going to divide it by your initial concentration, which here is 0.1. It's the only initial concentration you had. And you're going to multiply it by 100. Okay. So here we have our x value of 7 times 10 to the negative 6. We're going to divide it by 0.100. Okay, and we're going to get a very small number still. So that's great. We get 7 times 10 to the negative 3%. That checks out because it's below 5%. Any percentage that's below 5% means that we're clear to use this for our x value. So now we go back into our equilibrium row, and everywhere that we see an x, we substitute this number in. So We substitute that number in here. We substitute that number in here. We substitute that number in here. Now, this question only asked us to find the pH. Oh no, it wants us to find the H3O plus and the pH of this solution. Okay, that means that we don't necessarily have to solve numerically here. We have to focus in on this column. Okay, so we're going to take our 7 times 10 to the negative 6. That is our concentration of H3O plus. I'm going to fill in the other ones just for completion's sake. Okay. So my concentration of Cn minus is also 7 times 10 to the negative 6. And my equilibrium concentration of HCN is going to be you see what I mean when I say that it's so small, it basically doesn't affect it because it's 0.0999993. So if you were rounding this in terms of significant figures, it would round back up to 0.1 anyway. Okay, I'm just putting in everything that's in my calculator so we could see how similar this is to our initial value of 0.100. But we, like I said, we want to focus in on this value here, okay? Because this concentration tells us what our equilibrium H3O plus concentration is. All right. And if we know our equilibrium H3O plus concentration, then we can find the pH. I'll put a little equilibrium down there so we know that we're focusing in on that one. Okay, now to find the pH, we're going to do the negative log of 7 times 10 to the negative 6. And we got a pH of 5.15. Okay. So, it's pretty straightforward. I mean, it's all very logical, I think. So we'll try another one now. Okay, what was our question? Okay, we're finding the H3O plus concentration in the pH of 0.250 molar hydrofluoric acid solution. Okay, and our Ka is going to be 6.8 times 10 to the negative 4. Okay, so again, first steps here. We want to write out a representation of our reaction. Okay, so important to write this out for yourself so that you have kind of a good guideline set for your ice table. Okay, so we have aqueous hydrofluoric acid plus water. And that's going to give us, again, our hydrogen is going to come over here, form H3O plus, and it's going to leave behind the fluoride ion. And again, this is going to be this is like our star column there because this is the column that we need to solve for to figure out what the pH is. So we have our initial row, which is our 0.250 molar HF. It's annoying me. I'll fix that. Okay. And then our change. Okay, and again, we'll take this water section and we'll knock it out. Okay. Now for our initial amounts of H3O plus and our F minus will have zeros. And again, we're going to assume that our hydrofluoric acid is going to dissociate, meaning its concentration will decrease as it separates into ions. So we know that we're going to be losing some of that concentration as it forms hydrogen ions and fluoride ions. Okay, so we have 0.250 minus X, X, and X. All right, so our next step is going to be to set up our Ka expression, products over the reactants raised to the coefficients. Okay, so we have X squared over 0.250 minus X. And that's going to equal our Ka value of 6.8 times 10 to the negative 4. Okay, so with all your weak acids, you're at least going to try this X is small approximation every time. So we'll try to cancel it out and we'll see if we can solve that way. So I'm going to multiply 0.250 by both sides so I can get it out of the underneath of the fraction here. So for X squared, I'm going to have 6.8 times 10 to the negative 4 times 0.250. And I'm going to take the square root of both of those values. Okay, and I'm going to get 0.013. Okay. So now I'm going to do my 5% check. Okay. Say okay to you guys a lot, like you're actually talking to me right now. I think it's funny. So our 5% check is going to be our X value over our initial amount times 100. So 0.013 divided by 0.250 times 100. So let's see what it is. Oh, sad. 5.22. It's too big. Okay. That's too big. That means that we have to go back up top and we're going to solve this using the quadratic. Okay. Because 5.22% is above our 5% mark. And that's no good. No good. Okay. So we're going to erase this. Put that back in. Okay, and now we're going to have to go through solving for our quadratic. So I'm going to rewrite this as, I'm going to multiply both sides by the whole denominator here. So X squared is going to be 6.8 times 10 to the negative 4 times 0.250 minus X. And I'm going to distribute in there. Okay, so 6.8 times 10 to negative 4 times 0.250 is 1.7 times 10 to the negative 4 minus 6.8 times 10 to the negative 4x. Okay, and I'm going to move both of these things onto the left side so that all of my variables are on one side and I set my equation equal to 0. Okay, so I'm going to have x squared plus 6.8 times 10 to the negative 4x minus 1.7 times 10 to the negative 4. Okay, because I'm adding this to the left side and I'm subtracting this from the left side. And that would be equal to 0. Okay, and now I have the variable set for my quadratic because remember, that when you're doing your quadratic, A is going to be your x squared value, B is going to be your x value, and C is going to be your numerical value. So my A value is going to be 1. My B value is going to be 6.8 times 10 to the negative 4. And my C value is going to be negative 1.7 times 10 to the negative 4. Okay. Now I have the numbers that I need to plug into my quadratic equation, which is minus b plus or minus square root b squared minus 4ac all over 2a. Okay, so we'll plug in all of that. Okay, so we have b squared 6.8 minus 4 times 1 times negative 1.7 times 10 to the negative 4. And all of that is going to be over 2 times 1. Okay, so I'm going to solve out what's underneath that square root first, kind of like I did when we were looking at the quadratic in the last chapter. And I'm going to rewrite it down here. Okay, so we get 2.60. I'm just keeping a little bit of extra digits in here to because we're not going to really round it until the end. Okay, so I'm only going to solve for the plus here because if I solve for the minus, I'm going to have a negative x value, and we can't have negative concentration values. So we're going to kind of ignore this one. So this plus 6.8 negative times 10 to the negative 4 divided by 2 gives us 1.27 times 10 to the negative 2 molar for our x value. And again, in this case, our x value that we're specifically focused on is going to be our hydrogen ion concentration because that gives us our pH. Okay. Once we have that, we can solve for our pH. So negative log of 1.27 times 10 to the negative 2 is going to be a pH of 1.90. Okay. And we're going to run into a few more of those where we have to use the quadratic. But it gets very familiar, and then it's a pretty quick process. Once you're used to the method. So let's take a look at 2 more of these. Okay, I'll let you look at those while I erase my board. Okay, so here we have 0.2 molar HNO2 with a Ka of 4.6 times 10 to the negative 4. All right, so hopefully the process is pretty familiar now. First, we're going to set up our equation as a reaction with water. It's aqueous HNO2, liquid water, and it produces H3O plus and the nitrite ion. Okay, and then we could set up our ice table. Our initial amount is 0.200 molar HNO2. We're going to be losing our HNO2 and we're going to be producing hydrogen ions and nitrite ions. And then our equilibrium concentrations will look like this. Okay, so then we can set up our K expression. Products over the reactants, brace the coefficients, so we can set it up as a little more shorthand now. So we're going to set it up as x squared over 0.200 minus x. All right, and we're going to again try to approximate and get rid of that. Okay, so we see that to solve for x, we'll take the Ka value and we'll multiply it by 0.200. Okay, so 4.6 times 10 to the negative 4 times 0.200. Okay, and then we'll take the square root of these values to solve for x. Okay, and we get a value of 9.59 times 10 to the negative 3 as our x value. So we'll do our 5% check real quick. So we're going to take our x value, 9.59 times 10 to the negative 3, divided by our initial concentration of HNO2, which was 0.200 molar, multiply it by 100. All right, and we end up with a percentage of 4.80 this time, which checks out, which means that we can assume that this value here is okay to use for our x value. So from there, well, let's rewrite it properly. So we know now that our H3O plus concentration is going to be equal to our x value. So that'll equal 9.59 times 10 to the negative 3 molar. And then our pH will be negative log of H3O plus, or negative log of 9.59 times 10 to the negative 3. Okay. Okay, which is going to be 2.02. Okay. Let's look at that second example. See how much faster it is when we don't have to use the quadratic. It's nice. Change these two. Okay, so here we have 0.0150 molar acetic. I'm going to represent acetic acid as HAC because I don't want to write out the whole acetate ion. And you're going to see it represented like this pretty frequently anyway, so it's good to get used to. And the Ka value for acetic acid is 1.8 times 10 to the negative 5. Okay. But you can represent the overall weak acid reactions with water without using the formulas. Okay. If this represents our acetic acid, okay, our ionizable hydrogen will always be out front here. Okay, and we know that it's reacting with water, but the same thing is still going to happen. Our hydrogen is going to exit the acetic acid and attach to the oxygen and form H3O plus. And it's going to leave the acetate ion behind, and we can represent the acetate ion as AC minus, right? Because it's still the same formula, it just has an extra electron there. Okay. So our initial amount of acetic acid is 0.0150. We'll X off that stuff. Our change value is going to be minus X for the acetic acid and plus X for the H3O plus and the AC minus. And then we'll represent our equilibrium as 0.0150 minus X, X, and X. All right. Now we're going to go through our Ka procedure. So our Ka is going to be X squared over 0.0150 minus X. We're going to assume that this X value is small. We'll check it out when we're done solving for it, but we'll assume it's small to begin with. And that means that our X squared is going to be equal to Ka times 0.0150. Okay. So I'm going to multiply this out in my calculator using this Ka value. All right, I'm going to take the square root. Okay, so now I'm going to do my 5% check, where I take my X value divided by my initial concentration times 100. All right, and I got a percent here of 3.46, which is great. That means I can keep this X value. And we want to remember that this X value is going to correspond to our hydrogen ion concentration, which we're going to use to find the pH, right? So our X value is going to equal our H3O plus concentration. And I'm going to round this to my sig figs now. 5.2 times 10 to the negative 4 molar. And I'll use that concentration to find the pH. Get a pH of like 3.28. Oh, yeah, 3.28. Okay. So ice tables will help us find our X value. Our X value represents our hydrogen ion concentration. We use our hydrogen ion concentration to find the pH. Cool. All right. So the next couple examples that your textbook has for you are other examples where our X's small approximation doesn't work out. So we can look at those too, because I know that those sometimes those make people sad. So let's do one more of those just for practice, okay? Let me switch back to the whiteboard. Okay, so take a look at this one. Write down this info. We'll go through the process of still attempting that X's small approximation just so that you could see, like that's a process you should always start with. You should always assume that X is small. And, it's better to prove yourself wrong than to automatically default to the quadratic because the quadratic has a lot of room for error, okay? And you want to limit basically the steps that you do in a problem, because the more steps that you have to perform, the more likely it is that you accidentally make a mistake that will affect your final answer. And that's the real benefit of being able to use the approximation, is it cuts down on some of the math steps you have to do, which means you're less likely to run into making a mistake. I mean, we have a little bit of a spoiler here because we know that our approximation isn't going to work, but it's good to see it in action. So we have this HNO2 solution again that we're looking at. First step is always writing out this reaction for yourself and building your ice table based off of this reaction. Okay, so we'll put our initial concentration of the HNO2 over here. This will be our minus X. These will be our plus X's. And our equilibrium will be 0.010 minus X, X, and X. Okay, so again, we know that our Ka expression is going to be these two products multiplied by each other, divided by our reactant. Okay, and we're going to try this X's small approximation first. So we'll have our Ka times 0.010, because we'll multiply both sides by 0.010. And then we'll take the square root of that value. So our X value in this case is 2.14 times 10 to the negative 3. To do our 5% check, we're going to take X divided by the initial times 100. So 2.14 times 10 to the negative 3 divided by 0.010. And we get 21.4%. Okay, so like we were expecting, that's too high. Okay, so we can't discount this X in our Ka dissociation. All right, so we'll leave it there. Okay, I'm still going to go through that next step of multiplying both sides by this denominator, but I'm going to just multiply by the whole denominator instead. So I'll have Ka times 0.010 minus x equals x squared. And I'm going to distribute that Ka value into my parentheses. And remember, my Ka value is up here. It's 4.6 times 10 to the negative 4. All right, so let me rewrite that. So we'll say that x squared equals 6 minus. Okay. And now again, I'm going to readjust this so that both of these variables are on the same side as my x squared. I always leave my x squared positive, so I move everything to the same side as my x squared to keep that value positive. So I can rewrite this as x squared plus 4.6 times 10 to the negative 4x minus 4.6 times 10 to the negative 6. Okay. And from this, I'm going to pull my a, b, and c values out for my quadratic equation. All right, so I'm going to erase the stuff that's up here so I can write my a, b, and c. So my a value is going to be 1. My b value is going to be 4.6 times 10 to the negative 4. My c value is going to be negative 4.6 times 10 to the negative 6. And now I can do my quadratic. So we have minus b plus or minus square root b squared minus 4ac all over 2a. Okay, and we'll plug in all of our stuff now. So minus 4.6 times 10 to the negative 4 plus or minus 4.6 times 10 to the negative 4 squared minus 4 times 1 times, don't forget our negative sign here, negative 4.6 times 10 to the negative 6, all over 2 times 1, which is 2. Okay, so again, I'm going to solve for what's underneath. I'm going to solve out basically this expression. That's how I like to tackle these. And it helps me organize everything and, you know, find the right answers in the end. Like I don't lose things by accident. Okay, so I'm going to get this number and put over 2. Some people have questions about how to put this in the calculator too. If you have one of these calculators, I'll show you what I'm plugging in as I plug it in. If you have the TI-30X2S, you can plug it in, like hit the square root key and they give you a parentheses. Then you have to throw in an extra parentheses and do 4.6. You have to use your scientific notation key. Okay, so find that, because you have to be able to actually take this whole value and square it. And if you're not comfortable with that scientific notation key, then you might need to throw an extra set of parentheses around here. So you can take that value and square it, and that you're squaring the whole number, and you're not just squaring like this last part of it. Once you have that B expression squared, you're going to close this set of parentheses, and then you're going to do minus, and then in another set of parentheses for, I mean, you can put in the 1 if you want to, and then you're going to open another set of parentheses, negative 4.6 times 10 to the negative 6, close that parentheses, close this parentheses, and then close your big parentheses. All right, because it's a bit of a pain, but you could put it all in your calculator that way if you want to do it in one shot. Okay, otherwise you can just do it in pieces and keep good track of it. On my calculator, I start by putting in the 4.6. I'll move it over here so you guys can see it, maybe. 4.6 and the double E, because that gives me my scientific notation. And then I'm going to square that value. Then I'm going to hit the minus sign and then parentheses, 4 times 1 times 4.6 negative, because I have to make that negative. And then I'm going to use my scientific notation key again and have a negative 6 exponent. And I'm going to close my parentheses. And I get this value. Okay. And then I'm going to take the square root of that value. And I get 4.314 times 10 to the negative 3. And that's what I plug in over here. Okay. So then there are, you know, again, I have a negative B over here. So I'm going to discount this minus calculation because my concentration values can't be negative. So I'm just going to focus on the plus one. So negative 4.6 times 10 to the negative 4 plus 4.314 times 10 to the negative 3 divided by 2. So this is the calculation that I'm going to do. Okay, and I get an X value of 1.927 times 10 to the negative 3. I'm putting a molar after it because our X value is going to equal our hydrogen ion concentration that I was looking for, right? Because this equals X, X equals this. From here, I am going to plug this value in to find my pH. So it's going to be the negative log of 1.927 times 10 to the negative 3. I'm just keeping track of my sig figs as I go. All right, and I get a pH here of 2.72. Okay. Easy as that, guys. Easy as that. All right. Let's erase this. And then it looks like the next thing we're going to find is the equilibrium constant when we're given a pH value. So this is just going to be a different way to manipulate the ice tables. All right. So let's take a look at how we're going to do this. Just write down this information, how to switch markers, because destroying all my markers doing all these problems. All right, so we'll start with A. Yeah, 0.100 molar weak acid, which we're going to represent as HA, with a pH of 4.25. and we're going to find the Ka of that. These problems are great. I know these problems might seem like overwhelming at first or whatever, but this type of problem is so much better than, you know, finding those, like doing the ice table with the Ka value and trying to solve for the equilibrium concentrations. This is great because they're giving us that X value, right? We still want to start by writing out an equation that represents this reaction so that we can use it to build up our ice table. And this is what I was saying before, like it doesn't matter what your weak acid or your weak base is, you can just represent it with something like this. So when we write HA, we're saying that it's an acid because there's an H out in front. And this part is like the rest of the formula. Okay, so we have HA, it's reacting with water. And this hydrogen is going to ionize and attach to the water, form H3O plus. And it's going to leave behind the rest of that that anion. So that'll be our conjugate base over here. All right. Now here, they gave us the initial concentration of the weak acid. Okay, so that's going to be our 0.1 molar. We just sketch out this ice table. Okay. Right. And they also gave us a new piece of information here. They gave us the pH. Okay. Here is where it's important to remember that our pH is linked directly to our hydrogen ion concentration at equilibrium. Okay. So we can use the pH and we're going to be able to find H3O plus at equilibrium. Right. So to do that, we're going to do our H3O plus equals 10 to the negative pH. Oh, shoot. Let me grab that. Drop my calculator. All right, and we end up with a hydrogen ion concentration at equilibrium of 5.6 times 10 to the negative 5 molar. Now remember from our last set of ice tables, okay, when we were looking at these ice tables, you know, these values over here are our plus X values, and this value over here was our minus X value. So the fact that we just found our hydrogen ion concentration at equilibrium means that we found the value of X. So it's going to be 5.6 times 10 to the negative 5. Okay, and that means that over here, where we have our HA column, is that we can subtract X. So our equilibrium concentration of HA, it's no surprise it's going to be very close to 0.1, but we'll go through it anyway. It equals, I'm going to write down the number and then we'll put it to the right number of sig figs. It's 9.99 times 10 to the negative 2. right? So when we round that back up, it's going to be 0.1 molar again. All right, so these are our equilibrium concentrations. And just like in the last chapter, when we are calculating this Ka, we can only use equilibrium concentrations because K is just another equilibrium constant, even though it's attached to an acid in this question. All right, so to find our Ka value, it's going to be our product concentrations multiplied divided by our reactant concentration. I don't like to round until the very end here, so I'm gonna put in my full calculator value underneath here, but just I'm going to keep in mind that I'm going to have it to fewer sig figs. My final answer that I'm going to report, my final Ka value that I'm going to report is going to be the two significant figures. But I like to, I don't like to round until the very end in my calculations. Okay. All right, we end up with a Ka value of 3.1 times 10 to the negative 8. See, it's a nice problem. There's no quadratics there. It's pretty great. Okay, so let's try this with that second example. Try another one. Okay, so this time we have a 0.175 molar weak acid solution with a pH of 3.25, and we're going to find Ka. All right, so again, I start here with my balanced equation. Luckily, they're pretty easy to work out in your weak acid and weak base stage. It's not like when you're balancing the more complicated equations earlier in the textbook. Okay, we'll make up our ice table. Our initial concentration here is going to be 0.175. This will be minus X. This will be plus X. This will be plus X. And they gave us the pH value so we can find our H3O plus concentration at equilibrium. So we have 5.6 times 10 to the negative 4. That's our equilibrium hydrogen ion concentration. So that is also our X value. Okay, and then this value is going to be 1.75 minus 5.6 times 10 to the minus 4. Okay, and we get 0.174. All right, all our equilibrium values are plugged in. We're going to use this equilibrium row to calculate our Ka value. So we have 5.6 times 10 to the negative 4 squared divided by 0.174. So we have a Ka of 1.8 times 10 to the negative 6. Okay. Easy enough. All right, next question we're going to look at is, let me throw it up on the screen while I set up for the next problem so you can write stuff down, is we're going to find the percent ionization of these two solutions. Okay, so for A, we have 2.5 molar HNO2 with a Ka of 4.6 times 10 to the negative 4. And then for B, we have 0.25 molar acetic acid. C2H3. With a Ka of 1.8 times 10 to the negative 5. Okay, so let's take a look at this. You already know how to find the percent ionization. All right. The percent ionization is going to be that same calculation that you do to do the 5% check. Okay, that's going to be the same formula as your percent ionization. Okay, because you're going to go through and you're going to find that X value like we did in the earlier problems. And that X value represents your H3O plus that has ionized from your weak acid. So to check your percent ionization, you're just taking that X value, you're dividing it by your initial acid concentration, multiplying it by 100. So you can see what percentage of your weak acid actually separated into ions in solution. Okay, so you're going to see that the formula that we use, it looks exactly like this. All right, but first things first, and we are going to start with the same steps as before. So we want to write out an equation that shows our weak acid reacting with water. Okay, and then we're going to make our ice table. So our initial HNO2 concentration is going to be 2.5 molar. Cross out the water part. These are 0. This is minus X plus X plus X. And our equilibrium is going to be the combination of the two rows that came before our equilibrium row. So it's 2.5 minus X, X, and X. All right, and we're going to use the Ka value to solve this out. So Ka is going to equal X squared over 2.5 minus X. Okay, we're going to assume that this X value is very small and that we can discount it. So I'm going to rewrite this. I'm going to multiply both sides by 2.5 so that I can continue solving for x. So 2.5 times my Ka value is going to equal x squared. So let's do that calculation out. Okay, so I have 1.15 times 10 to the negative 3 equals x squared. I'll take the square root of that. And I get 3.39 times 10 to the negative 2 as my x value. And again, my x value is equivalent to my H3O plus value at equilibrium. Okay. Now, the formula that you see in your book to find percent ionization, you know, they write it a little bit differently, but it's the same formula. We'll call it percent ion. Percent ionization, we're going to take the concentration of your H3O plus at equilibrium. We're going to divide it by the concentration of your weak acid, whatever it was initially. And we're going to multiply it by 100. Okay. So again, all that breaks down to is your x value divided by your initial value times 100. Okay, so when we plug this in, we have 3.39 times 10 to the negative 2 divided by 2.5 times 100. And we get a percent ionization here of 1.4%. Okay, so this right here, that is our percent ionization. And all that means is what percent of our original weak acid actually formed ions. And we would expect with K values that are very small, that our percent ionization would also be very small. All right, so let's try question B, where we're just going to be looking at a different solution, but we'll just repeat the process to kind of drive it home. I need an ice table stamp that's made out of dry erase markers, so I don't have to keep on drawing out these ice tables. All right, so we have acetic acid that I'm going to represent like this, plus H2O gives me H3O plus, and my acetate ion this will be 0.250 molar. All right, so our equilibrium rho is going to look like this, 0.250 minus x, x, and x. All right, and we'll set up our K expression. It's going to be x times x divided by 0.250 minus x. We're going to assume that the amount of ionization is small enough that we can discount this value from our equilibrium concentration of the acetic acid. All right, and we're going to rearrange this and solve it for x. So x squared is going to be equal to Ka times 0.250. And my Ka value for acetic acid is this one up here, the 1.8 times 10 to the negative 5. My x squared value is going to be 4.5 times 10 to the negative 6. Take the square root of that. X will equal 2.12 times 10 to the negative 3. And remember that my x value represents my H3O plus concentration at equilibrium. Okay, so now I'm going to find my percent ionization. By taking my H3O plus concentration. So that's going to be my 2.12 times 10 to the negative 3, dividing it by my initial concentration of 0.250 and multiplying it by 100. Okay, and I get a percent ionization here of 0.85%. Okay. So that's all the percent ionization is. It's pretty straightforward. Let's see, what do we have next? Ooh, this one will be fun. So this next question is going to require some thinking. These questions we'll kind of look at together. Okay, so here we're looking at what happens when we mix together different weak acids. All right, now when we are mixing together acids that have a different degree of strength, and remember that when we're talking about strength in terms of acid and base reactions, that we are talking about their level of ionization. So we're going to equate the strength of an acid to the size of its Ka value. So stronger acids gonna assume that you wrote that stuff down. So stronger acids have higher Ka values, or larger, I would say larger Ka values instead of higher. Okay. And if you are mixing together two different weak acids, and one of them has a significantly larger Ka value than the other one, then whatever happens, whatever's happening with the larger Ka value acid, that's what's going to determine the pH of your solution. The acid with the larger Ka value is going to kind of overpower any of the other weaker acids that are in the solution. So in this question, they're giving us two acids. They're giving us 0.3 molar HF and 0.1 molar HClO. All right, and our HF has a Ka of 6.8 times 10 to the negative 4, and our HClO has a Ka of 2.9 times 10 to the negative 8. All right, so this equilibrium, this is going to determine the pH of our overall solution, because whatever hydrogen ions are released from the HClO, it's going to be such a small amount when we compare it to the hydrogen ions that are released from the HF that it's not going to even change our calculation. So we can base our entire calculation off of this dissociation here. All right, and we're going to do that. So we're going to write out the reaction of HF with water. Okay, and we're going to make an ice table to calculate our pH here. Okay, so we have 0.3, 0, and 0 minus x plus x plus x. Okay, so we're going to set up our Ka expression. So it'll be x squared over 0.300 minus x, and we're going to assume that this minus x number would be small enough that we could discount it from our calculation. All right, and we'll solve for x with the rest of our information. So we have Ka, and our Ka for HF is 6.8 times 10 to the negative 4 times 0.3 equals x squared. So we get 2.04 times 10 to the negative 4 equals x squared. We'll take the square root of that. And we get 1.428 times 10 to the negative 2 as our x value. And remember that our H30 plus value at equilibrium is equal to our x value. So we just found our hydrogen ion concentration. Okay. Now that we have our hydrogen ion concentration, we're going to find the pH using it. So our pH is going to be the negative log of our H30 plus. So it'll be the negative log of 1.428 times 10 to the negative 2. So our pH is going to be 1.85. Okay, we're up to 2 decimal places here because even though I wasn't underlining the sig figs as I went through, this Ka value has 2 sig figs. So when I solved out this concentration for our hydrogen ion, that value is to 2 sig figs. So when I take the negative log of something with 2 sig figs, the answer is going to have 2 decimal places. All right. Okay, so now we're going to look at the second part of this question, which I thought was interesting. That's why I included it. Let's put it back up there. So now it's asking us to find the, if we're mixing these two things together, they're asking us to find what the concentration of that ClO minus ion would be. Okay, so we still have the same mixture, but we want to focus in on the ClO minus ion and what that concentration would be. And now we're going to see how the addition of this other acid affects what's happening with the weaker acid of the two. Okay, now we want to remember our hydrogen ion concentration value. That's going to become important. So we'll write it, I'll erase this part up here. So we know that our pH is going to be 1.85 and our H30 plus is going to be 1.428 times 10 to the negative 2 molar. All right, so now we're going to see what's happening with our HClO. We can write out another equilibrium reaction for our HClO with water. Okay, we're going to form our H30 plus and our ClO minus, but our initial row in this case is going to look different than it normally does. okay? And that's because we have this extra source of hydrogen ions here. Normally, when we write out our initial rows, we look at the original concentration of our weak acid, and that's it. We're done, right? But that's not true in this case because we have the 0.1 molar HClO, but we also have this HF that's in our solution. And we already know that the concentration of the hydrogen ions that it produced is this value of 1.428 times 10 to the negative 2. Okay. Our ClO minus initial concentration is still 0 because there's no extra source of the ClO minus ion. Oh man, did all that talking and the stupid screen was still up. So hopefully you could still follow along. There's my initial HClO. And for my H3O plus initial concentration, that's where I'm going to put in the hydrogen ion concentration that came from the ionization of the hydrofluoric acid. Okay. There's no extra source of my hypochlorite ion, so I can just leave, oh, not as X, I can leave that as 0. Because I don't have any other source of that. All of it's going to come from the separation of the HClO. All right. As long as these values are in place, now I can go through the rest of my steps, filling in that ice table per usual. My change for the HClO minus is going to be a negative change. I'm going to try to use some of this up and produce my product ions. Okay, and so my equilibrium row is going to look like this. Okay, my K expression, remember I'm going to use my K value for my HClO here. It's going to be products over the reactants raised to the coefficients. So it's going to be 1.4 times 10 to the negative 2 plus X times X and divided by 0.100 minus X. Okay. And we are again going to make that assumption that this X value that we're adding on to 1.4 times 10 to the negative 2 and that we're subtracting from 0.1, that this X value is going to be so small in comparison to the numbers that we're adding and subtracting, the 2 or from, that we can not count them in our calculation. Okay, so we're going to just, the plus X and the minus X, we're going to get rid of. And we're going to solve for this remaining X value. Okay, so we're going to rewrite this as Ka times 0.100 equals 1.4 times 10 to the minus 2 X. Right, and we're going to solve for X. So it's divided by 1.4 times 10 to the negative 2. Got a fatter marker, but now my handwriting is even sloppier than usual. Okay, and remember this is our Ka value that we're using. So 2.9 times 10 to the negative 8 times 0.1 divided by 1.4 times 10 to the negative 2. And I end up with 2.1 times 10 to the negative 7 as our X value. And that's going to be equal to the concentration of our hypochlorite ion. Okay. was a little bit more complicated, but you know, we can reason these things out. All right. Oh, so we're going to look at some bases next. So take a look at this. And then we'll try these ones out. So we're going to be looking at finding the OH and the pH of strong bases. Okay, and it's interesting, like this question is interesting because, you know, when we're looking at strong acids, a lot of times we look at a lot of acids that are monoprotic acids. For our strong acids, we only have one acid that's diprotic when we're looking at our 6 strong acids, and that's sulfuric acid. But with our strong bases, we have 3 strong bases that only have one hydroxide ion that ionizes. And we have 3 strong bases where 2 hydroxide ions ionize. And, you know, when we double that amount of hydroxide that gets ionized, we have to reflect that when we're talking about our hydroxide ion concentration. Okay, if we don't reflect that in our hydroxide ion concentration, then we're going to throw ourselves off in terms of our pH calculations. All right, so let me show you what I mean. So we're going to start with the easy one. They give us 0.225 molar KOH. All right, when you're dealing with bases and trying to figure out the pH or the hydroxide ion concentration from a strong base, the first thing you need to do is look at the ionization of the base. Okay, so you have to write out, you know, in water, this is going to ionize and it's going to form 1 potassium ion and 1 hydroxide ion. You want to verify that there is a 1-to-1 ratio between your KOH and your hydroxide. Okay, as long as there is, that means that your OH minus concentration is going to equal the concentration of your KOH, which will equal 0.225 molar. All right, from there, you have the 2 roots that you can take to solve for the pH. You can convert this to H plus using your KW. And then you can find the pH from the H plus. I'm going to do it the other way. So I'm going to find the POH from this. So I'm going to take the negative log of my OH minus concentration. Okay, so my POH is going to equal 0.648. Okay, not my final answer because this did not ask me for my POH, it asked me for my pH. So now that I have my POH, I'm going to solve for my pH. 14 minus my POH. Right? Remember that from before? So my pH is going to be 14 minus 0.648. So my pH is going to be 13.35. Right? Okay, we can solve it this way for the next one just so that we can see both of them back and forth. So the next question asks us to look at 0.0015 molar strontium hydroxide. Okay, and this is one of the cases where if you do not look at the dissociation of the strong base and understand that we have more hydroxide ions than we had in the last solution, you're going to end up with a skewed pH value overall. Okay, so when strontium hydroxide dissociates in water, it's going to form one strontium ion, which is Sr2 plus, and it's going to form two hydroxide ions. Okay, so that means that there's a 1 mole to 2 mole ratio between our base and our hydroxide ion. So that means that if we have 0.0015 moles of SrOH2, every 1 mole of SrOH2 is going to have 2 moles of OH minus. All right, so we're going to end up with 0.0030 moles of OH minus per liter of our solution. Okay, I mean, you can simplify this for yourself and say that you have to double this value, but I just wanted to show you in more of like in a mathematical way what we're doing here. Okay, so the concentration of our hydroxide ion in this solution is going to be 0.0030 molar. All right, from here, we're going to find our H plus concentration using our relationship with Kw. All right, I told you that we can use the different method for this one. So that'll be 1.0 times 10 to the negative 14 divided by 0.0030. So our H plus concentration is going to be 3.3 times 10 to the negative 12 molar. Okay. From here, I want to find my pH. So that'll be the negative log of my H plus concentration, which will be the negative log of 3.3 times 10 to the negative 12. And that's going to give me a pH of 11.48. All right. Let's look at one more of these examples. Another one where we have that extra hydroxide ion. Okay, so here we're looking at 0.010 molar barium hydroxide. Okay, when barium hydroxide ionizes in water, it's going to form one barium ion, which is Bi2+, and it's going to form two hydroxide ions. Okay, so if we have 0.010 molar barium hydroxide, that means that our hydroxide ion concentration is going to be 2 times 0.010 molar. Okay. That's our hydroxide ion concentration. Okay, so I'm going to find the POH from this value, which will be the negative log of my OH minus. Okay, which is going to be 1.70. And then my pH will be 14 minus my POH. which will be 14 minus 1.70. And that's going to be 12.30. All right. Let's erase this. The next questions we are going to end up looking at have to do with weak bases. So those will be fun. Okay, so here is our next set of problems, and you see here we're working with you could tell they're weak bases even if you didn't know right off the bat, because we're given the K values for them. And like I mentioned before, you're only going to have a Ka or a Kb value when you're looking at weak acids or bases, not strong ones, right? So we will go through both of these examples, and we should see that working through them, it's very similar to the method that we used for solving for the pH of acids. What we want to focus on here, though, is the final step of our calculation when we're looking at weak bases, because we have to make sure that we are solving for the pH during our last step and not the pOH. Okay, and I'll explain more about what I mean by that when I get to the end of this this calculation set. All right, so let's just write down some of this info. Okay, and so for this first question, we want to solve for the hydroxide ion concentration of the solution and then find the pH. Those are the two questions we're being asked. We're going to start with the same first step. Okay, same exact first step that we did before. We're going to look at this base and we're going to see how it reacts with water, and we're going to write ourselves a reaction. Okay, so we have NH3 plus H2O. And we see that in this reaction, when we have a base instead of an acid, our base acts as a proton acceptor instead of a proton donor. Okay, so we are going to, like, the NH3 is going to pick up one of these hydrogens from the water, right? A proton is going to move over, and it's going to form NH4 plus. And it's going to leave behind, when the proton moves over, it's going to leave behind a hydroxide ion. Okay. So we can start formatting our ice table from this reaction. And one thing that you should notice right away, as a difference between our acid reactions and our base reactions, is the existence of the hydroxide ion as one of the products. Okay. When we have a weak acid reaction with water, we are going to end up producing H3O plus as one of our products. When we have a weak base reacting with water, we're going to end up producing hydroxide ion. Okay. When we have hydroxide ion as one of our products, instead of using a Ka value to solve for our concentrations, we're going to use a Kb value. And that's because, remember, Ka is going to relate to acids, right? The A is for acids there. And we represent acids using the H3O plus, or the H plus ion. We use our Kb values for bases, right? B for bases. And bases are represented by OH minus. So when we see a hydroxide ion in our reaction, we want to focus in on that Kb value that corresponds. Okay. We write a KB expression the same way we write any other equilibrium expression. KB is going to be products over the reactants raised to the coefficients. So in this case, it's going to be NH4 plus times OH minus divided by NH3. And we leave liquid water out. All right. So let's fill in what we can with our ice table here. We're starting with an initial concentration of NH3 of 0.100 minus X plus X plus X. And for equilibrium, we have 0.100 minus X, X and X. Okay, so when we set up our KB expression now, we have 1.76 times 10 to the negative 5 equals X times X, or X squared, over 0.100 minus X. Okay, and again, I have this K value is very small, so I'm going to assume that this X is small, and we'll check it before we move on. Now I'm going to multiply both sides by 0.100. So I'm going to times 0.100 just so you know what I'm doing here. And we'll rewrite this. X squared equals then we'll take the square root. Okay, and this is the part where we have to be careful with the information that we've just solved for, okay? Because unlike in our weak acid reactions, when we are solving for our weak bases and we calculate this X value, what we are calculating for is this X or this X, but you know, we want to focus on the variable that can help us calculate the pH. And we can find the pH through our OH concentration, but we have to remember that this is an OH minus concentration. It's not H plus. Okay. So we can't solve for pH directly from this number. Okay, before I move on, I'm just going to do my 5% check really quickly. So I'm going to take my X value and divide it by 0.1, multiply it by 100. You always want to just double check this. Okay, and it's 1.33%, so that's fine. So now we know that we can use this X value. So this X value, put a little arrow over here. This is going to represent our hydroxide ion concentration. Okay. From our hydroxide ion concentration, we can find the POH. Okay, so we're going to do the negative log of our hydroxide ion concentration. And we have a POH value of 2.88. Okay, not our final step. To find our pH value, we are going to do 14 minus POH. So 14 minus 2.88. And we get 11.12. So this is our pH. So this is our OH minus concentration. This is our pH. Okay, so you just want to be really clear on that final step. We have to always remind ourselves what this X stands for. When we solve for X and we're working with a basic solution, that X represents our hydroxide ion, not our hydrogen ion. Okay, let's move on to that second question. Here we're given, I'm going to put it back up on the screen just so you can remind yourself of what we're given, because we're given a Ka value here instead of a Kb value, even though we're working with a base. You know it's a base because it has that amine term in it, and your amines are going to be basic. So let's write down the info. Okay. I mean, so right away, I mean, we're working with a base here. We're given the Ka value of its conjugate acid. So the first thing that I want to do here is, I don't know, I guess the first thing I'm going to do is the same thing that we've always been doing, just so we don't confuse ourselves. And let's write out a reaction for this with water. And then maybe our next step will make sense to us. Okay, so let's take the methylamine. Add some water. And we see that one of these hydrogens is going to attach itself to the nitrogen there and form CH3, NH3 plus, and it's going to leave behind a hydroxide ion. Okay, so like I said before in the last example, when you write out your reaction of your weak acid or your weak base with water, and you have hydroxide ion as one of your products, this means you're going to need to use a Kb value to solve your ice table. Okay, you have to use a Kb value if one of your components is hydroxide. Right? This means that we have to find the Kb value from the Ka value we were given. Okay, so one of the relationships that we talked about before was the fact that we can relate Ka and Kb to one another via Kw. So if I want to find the Kb value, divide both sides by Ka. So my Kb value is going to be Kw divided by Ka. Okay, or 1 times 10 to the negative 14 divided by 2.27 times 10 to the negative 11. Okay, and I get 4.4 times 10 to the minus 4. That's going to be the Kb for my CH3NH2. All right. Now that I have a Kb value, I'm going to work on filling in my ice table. I'm starting with 0.33 molar methylamine. I'm going to be decreasing the concentration of my methylamine and forming the conjugate acid and the hydroxide ion. Okay, my Kb expression, I'm going to set up as 4.4 times 10 to the negative 4 equals x times x, or x squared. over 0.33 minus x. I'm going to assume that this x that I'm subtracting from 0.33 is going to be a small value. So we'll cancel it out of our calculation to make it a little bit easier. And I'm going to multiply both sides by 0.33 so I can solve for x. Okay, so I have 1.452 times 10 to the negative 4 equals x squared. And I'm going to take the square root of that. And I get 1.205 times 10 to the negative 2 equals x. And remember, this x value represents our hydroxide ion concentration when we're in a basic solution. All right. Let's just double check our 5% rule. So I'm going to take this value and I'm going to just divide it by 0.33 and multiply it by 100. Okay, so my percent equals 3.65. So I can continue to use this x value. Okay, so this is my hydroxide ion concentration. I can plug it in here if I want. But one of the values that I was looking for, I've successfully calculated now. Okay. Next, I am going to find the pH. All right, so I'm going to find the pH again through the POH. So to find the POH, I'm going to take the negative log of my hydroxide ion concentration, right, which is this number. So my POH is going to be 1.92. My pH is going to be 14 minus my POH, which is going to be 12.08. Okay, so there's my pH value. There's my hydroxide ion value. And that's how you work with weak bases. All right. Let's see what we're looking at next. Okay. This next topic requires a little bit of explanation. So let's talk through some of this. I put up the strong acid list for reference here because we're going to need it in some of our determinations. Okay, so maybe I'm going to rewrite our strong acids up here. I mean, I can't stress enough how much you guys need to know the strong acids and the strong bases by heart. You really don't want to be walking into the exam not feeling 100% sure about that. There's too many questions where that knowledge is like your foundation work for the question. And this is going to be kind of an example of that. So this question asks us to classify the anion as a weak base or neutral. Okay, and you should be able to tell based on what the ion is, whether it is basic or neutral. All right. This is less panic inducing if you know what the strong acids are, because there's a pretty easy way to go about that process. All right. So for the first, let's look at the first two as like a pair, because they go well together. So we're looking at NO3 minus and NO2 minus. Okay. Now, you want to see what type of acid forms when you combine your anion with a proton. Okay, that's going to tell you whether your anion is basic or neutral. Okay, so if I combine HNO3 with a proton, it's going to form HNO3. HNO3 is one of our strong acids. Agree? So we could say that NO3 is going to be the conjugate base of a strong acid. The counter ion to your strong acid, or your conjugate base of your strong acid, is always pH neutral. Okay? The conjugate base, I'm going to abbreviate it as CB, the conjugate base of any strong acid is neutral. Okay, so if you want to think about it kind of simply, there are only 6 anions that you have to know that would be considered pH neutral. All right, the rest of them are going to have basic tendencies. So our HNO2 minus, if we added a proton to that, is going to form HNO2. This is not a strong acid. Okay, that means that NO2 minus is the conjugate base of a weak acid. Conjugate bases of weak acids are always weak bases. Okay, so that's how this trend works. All right, so now we can look at the remaining 3. Okay, so we have C2, H3, O2 minus, CHO2 minus, ClO4 minus. Okay, so if I add a proton onto my acetate ion, I end up with H, C2, H3, O2. Not a strong acid. That means that this acetate ion is basic. Okay, CHO2 minus will give me H, HCHO2. This, not a strong acid. So my ion is basic. ClO4 minus gives me HClO4. Ding ding. Strong acid. That means that the perchlorate ion is pH neutral. Okay. Now we're going to look at the same setup with our cations. Okay, we can look at cations and we can determine whether they're acidic or not the same way. Okay, but we'll list out our strong bases for this one. And there's a Yeah, and we'll list our strong bases, and that'll be enough. SB. All right, so there are our strong bases. So this is going to work similarly to the trend last time, except we're going to look and see whether adding hydroxide to the cation we're looking at gives us one of our strong bases back out. Okay, so C5, H5, NH plus. So if I add hydroxide to this, am I going to form one of my 6 strong bases? Nope. I'm going to write it as, I'm going to phrase it a little differently. Okay, so we'll say it doesn't form a strong base. Okay, if it doesn't form a strong base, that means that the cation is going to be acidic. Okay, the counter ions to strong acids and strong bases are the only neutral ones. So for B, we have the calcium ion. Okay, so if we added, I'm putting 2 hydroxides here because we have a positive 2 charge, and we have to, balance the charge out. But you see already, right? If I have calcium and then 2 hydroxides, I'm going to end up forming calcium hydroxide, and calcium hydroxide is a strong base. Okay, so the counter ion of a strong base is going to be neutral. Okay. For part C, we have Cr3 plus. So if I added 3 hydroxides to this to counteract the charge, I end up with CrOH3. Chromium hydroxide is not on my strong base list, right? If it's not a strong base, that means that the cation is an acidic one. Okay, and 2 more examples. Oh, 3 more examples. Okay, for Li plus, right, if I add an OH minus to that, I'm going to form lithium hydroxide. Lithium hydroxide is a strong base. And that means its counter ion is acidic. Oh, just kidding, guys. Counter ion of strong bases are neutral. Okay, I was looking at this thing that was supposed to be an O and it looked like an A and it was bothering me. It still looks like an A. Oh well. Anyway, lithium hydroxide is a strong base. The counter ion to a strong base is pH neutral. For CH3 and H3 plus, again, this is not going to form a strong base. And that means that this is going to be acidic. And our last one, Fe3 plus. This is also not a strong base. And you also see it, you also see that when you have small, highly charged metal cations, that's another way that you can tell that a cation is acidic. And in the case of the iron ion, as well as that chromium 3 plus ion that we looked at, these are both examples of these small, highly charged metals. And those act as weak acids in water. But if we look at how they combine with hydroxide, that's another good indication, because we can see that the bases that they would form are not one of our 6 strong bases. Now we're going to look at something a little bit different. Still using the same kind of techniques. We're going to look at these compounds and see whether they would form acidic, basic, or neutral solutions if they dissolved in water. Okay, and we're using the knowledge that we just went through to figure this out. Okay, so we have to go through, okay, just, write these down for yourself. And you're gonna go through like a stepwise process here. So starting with the strontium chloride. First, you're gonna break this up into its ions. Okay, so we have a strontium ion and we have chloride ions. You're going to take the cation and see if it creates a strong base when you add hydroxide to it. So if I have the strontium ion and I form a base with it, I end up with SrOH2. Okay. I'm going to do the same thing now for the Cl minus, but I'm going to be adding hydrogen ions to it. Hydrogen ion plus the chloride ion is going to form HCl. Okay, so now you're going to go back to your lists of strong acids and bases and see if these are strong acids or strong bases. Spoiler, they are. This is a strong base. This is a strong acid. Okay, so if this is a strong base, that means that this strontium ion is neutral. If this is a strong acid, that means this chloride ion is neutral. That means that this compound, if it's neutral, a neutral ion plus a neutral ion, the compound overall is going to be neutral. Okay, so it's not going to be acidic or basic when it dissolves in water. Okay, let's look at the next one. The next one is AlBr3. Okay, so when this dissociates, it's going to form an aluminum ion, and it's going to form bromide ions. Okay, now you can look at the combination with some hydroxide ions here and see that it forms a base that would look like this, right? That is not a strong base. You can also see that it's, again, we have a small, highly charged cation, or metal cation. And that is one of the examples of cations that behave as acids in solution. So even if you didn't prove it to yourself by seeing whether or not it formed a strong base, you could look at this and say, well, I have a small metal with a pretty high charge, so that's probably going to behave as an acid. Regardless, once you go down and you see that combining it with hydroxide does not form a strong base, then you know that this ion is going to be an acidic one. right? For your bromide ion, we're going to see what happens when we add some hydrogen ions to it. That would form HBr. HBr is going to be, HBr is a strong acid. That means that your bromide ion is going to be neutral. When you have an acidic ion and a neutral ion together in a solution, your overall solution is going to be acidic. Okay, so we have, the next one is CH3, NH3, NO3. Okay, and this is going to break up into CH3, NH3 plus, and NO3 minus. Okay, if I come over here and I add a hydroxide to this, I'm going to end up with this. This is not a strong base. That means that this ion here is acidic. If I add hydrogen ion here, I'm going to form HNO3. This is a strong acid. That means that the counter ion to that strong acid is neutral. All right, so again, if I have something, if I have an acidic cation and a neutral anion, acidic plus neutral is going to give me an overall acidic pH. Okay, let's look at the next one. We have NaCH02. This is going to form sodium ions and a CHO2 minus ion. If I add OH minus here, I'm going to get NaOH. That's a strong base. That means that my sodium is going to be neutral. For my CHO2 minus, if I add a hydrogen ion, it forms HCHO2. That is not a strong acid. That means that this anion here is basic. So if I have a neutral ion mixing with a basic ion, my overall solution is going to be have a basic pH. Okay. My last example involves like the most work out of all of them. So I have NH4F. And when this ionizes, it's going to form NH4 plus ions and F minus ions. Okay. I see that if I combine my NH4 with a hydroxide ion, I'm going to form NH4OH. If I add hydrogen ion to this, I'm going to form HF. This is not a strong base. Okay, which means that the NH4 plus is acidic. And this is not a strong acid. Which means that my F minus ion is going to be basic. Okay, so I'm going to have to compare the Ka and Kb values of these things to determine whether my overall solution is acidic or basic. Okay, so I want to look up the Ka of ammonium. Okay, you can look up this value in a table. And I want to look up the Kb of F minus. Okay, and these are values that you can look up, or you can look up the Ka of hydrofluoric acid and then find the Kb of the fluoride ion from that, because Ka times Kb equals Kw. You can do the same thing for ammonium if you only had, for example, the Kb of ammonia. You can use that to find the Ka of NH4 plus. If you only had the Ka of hydrofluoric acid, you could use that to find the Kb of the fluoride ion. Okay, but these are in tables for you. So if you look at the Ka of ammonium, it's going to be 5.68 times 10 to the negative 10. If you look up the Kb for the fluoride ion, it's going to be 1.5 times 10 to the negative 11. Okay, and you're literally going to compare these two values and see which one's larger. The larger one wins. Okay, so in this case, my Ka value is greater than my Kb value. That means my solution is going to be acidic overall. Okay, let me move that up a little bit. If my Kb value had been larger, then my overall solution would have been basic. All right. So now we're going to look at some problems that involve these compounds, like the ones we just looked at, that when we dissolve the compounds in water, it affects the pH of the solution. Okay, so specifically here, they're already telling us this, so that's helpful. They're telling us here that we're looking at a compound that when we dissolve it in water, it's going, its anion is going to act as a base. And we need to figure out what the pH of that solution is. All right. So let's write down that info and then take a look at the problem. All right. Now, the first thing you want to do is look at the compound that you're given to start with, and you want to see what happens to it when you dissolve it in water. Okay, so if I have NaCHO2 and I dissolve it in water, I mean, basically what's going to happen here is that my sodium ion is going to ionize, right? I'm going to end up with some Na plus. I'm going to end up with some CHO2 minus, and I'll still have some water in my solution. Which is why we, when we're writing dissociation reactions, we usually leave the water out. But what we're focused on are these ions here. Okay, so just like we went through last time, if we look at these two ions, we can tell that the sodium ion is pH neutral because when it reacts with hydroxide, it forms a strong base. So we know that the sodium ion is not going to affect the pH of the overall solution. But this ion it will, because HCHO2 is not a strong acid. Okay, so we have to focus in on the reaction of this basic anion with water. So we have to take our basic anion, okay, and we have to see how it reacts with water. What's going to happen? One of the hydrogens is going to pop off and come over here. So it's going to form HCHO2. And it's going to leave behind a hydroxide ion. Okay. And once we go through that first step of breaking up our initial compound, finding the anion that's going to change the pH of the solution, and using that as the starter for our pH reaction, the rest of it proceeds like a regular ice table and a regular pH calculation. Okay, so this is all going to look very similar to what we've already done. We have an initial concentration of 0.100 molar because when this dissociates in solution, it's in a 1-to-1 ratio. So if I have 0.1 molar of my original compound, I'm going to have 0.1 molar of my basic anion. Okay, and I'll have none of that to start. Minus x plus x plus x. Okay, I'm looking at this reaction right here and I see that I have a hydroxide ion as one of my products. So I know I'm going to need a Kb value to solve this. I was given a Ka value, so I'm going to need to find the Kb value from that. So Kw equals Ka times Kb. So divide both sides by Ka. So 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4 is going to give me my Kb value. And I get 5.56 times 10 to the negative 11. So now that I have my Kb value, I'm going to set up my K expression. So 5.56 times 10 to the negative 11 equals my products, x times x, or x squared, divided by my reactant, raised to any coefficients, but there aren't any. I'm going to assume that this x value is small enough that I can remove it from my calculation, and I'll double check that. And now I'm going to solve for x, just like we were doing before. I'll take the square root here. So I'm solving for x, and x, remember, is going to represent my hydroxide ion concentration. Again, once I solve for this value, I'm just going to divide it real quick by my initial amount. I'll write it over here so that it's separate, so I'm not messing around with that. So we'll do our little 5% over here. 2.36 times 10 to the negative 6 divided by 0.1 times 100. And we get 2.36 times 10 to the negative 3%. So that checks out. That means that we can use this value here for our hydroxide ion value. And that means that we can use it to solve for POH and then pH. Okay, so my POH is going to be the negative log of OH minus. So negative log of 2.36 times 10 to the negative 6. That's going to be 5.63. Okay, and now I'm going to find the POH from that. Or I'm going to find the pH from that using the POH, sorry. So pH equals 14 minus POH, which equals 14 minus 5.63, which gives me 8.37. Okay, so there is my pH value of this solution. A little bit basic, which is what we were expecting, given the identity of the anion we were looking at. Okay? All right, I think we have another one of these that we can look at. Yeah, we'll look at one more of these, and then we'll look at a polyprotic acid. Let me just show you the problem real quick. So here we're going to find the pH of an aqueous 0.250 molar NaC2H3O2 solution. And the Ka of HC2H3O2 is 1.8 times 10 to the negative 5. You're constantly going to be given Ka values when you need a Kb value. So just be on the lookout. The best way that you can figure out for yourself whether you need a Ka value or a Kb value is to write out that reaction with water that we were talking about. Okay. But starters, we're going to look at the sodium acetate and we're going to see how it separates in solution. And we see that it forms a sodium ion and it forms an acetate ion. This sodium ion is going to be neutral because its counter ion is a strong base. This acetate ion is going to be basic because its counter ion or its conjugate is a weak acid. And weak acids have basic conjugates. Okay. Okay, we also know that if we have 0.250 molar sodium acetate, that molarity carries over here to our ion because they have a 1-to-1 molar ratio. Okay, so now I'm going to take my basic anion and I'm going to see how it reacts with water. So C2H3O2 minus plus H2O. Okay, I'm going to get HC2H3O2 plus OH minus. Okay, and again, what I tell you before, I'm going to keep telling you. You see this OH minus in your products? Means you need a Kb value. If you try to use your Ka value, you'll get a number. It won't be the right number. So when you see that hydroxide in your products, make sure that you're working with a Kb value. All right, set up our little ice table to keep track of everything. We have an initial concentration of 0.250 minus X plus X plus X. All right. Let's find our Kb. It's going to be equal to our Kw value divided by our Ka value, which is 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So our Kb here is 5.56. This seems familiar. 5.56 times 10 to the negative 10. Okay, that's the Kb we're going to use to solve the problem. So now we're going to write out our Kb expression so we can solve for x. So we have 5.56 times 10 to the negative 10 equals x squared, right? Because those are our products, x times x, divided by our reactants. We're going to make our assumption that this x that we're subtracting from the 0.250 is small enough that we can remove it from the calculation. And now we're going to solve for x. So I'm going to multiply both sides by 0.250. Okay, I get 1.39 times 10 to the negative 10 equals x squared. Take the square root of this, and I get 1.18 times 10, oop, I'm below my, there we go, equals x, and again, x equals our hydroxide ion concentration over here. We cannot forget that. Okay, let's do our 5% check real fast. I'll just tuck it in over here. So we're going to do our x value, 1.18 times 10 to the negative 5 divided by 0.25 times 100. Right, and we get a percent of 4.7 times 10 to the negative 3, which is well below, no, it's hard to say. It says 4.7 times 10 to the negative. It's really small. It's well below 5%. So we can keep rolling with this as our hydroxide ion value. Okay, from this value here that represents our hydroxide ion, we're going to use it to find our pOH. I like writing out all the steps for you so you don't forget them. Oh man, where'd you get that value? Okay, so I have a pOH of 4.93. Now to find my pH, I'm going to do 14 minus pOH, or 14 minus 4.93. And I get a pH of 9.07. Okay. All right. Okay, we're going to look at one more problem. Okay. Let me put it up while I erase it so you could start looking at it. So in this problem, we're looking to find the pH of ascorbic acid. And ascorbic acid is a polyprotic acid. Okay, hopefully we remember what a polyprotic acid is. It means it has more than one ionizable hydrogen, so it can contribute more than one proton to a solution. The formula for ascorbic acid is H2 C6, H6, O6. Okay. Now you see we have two Ka values. Okay. It's important to look at these two Ka values when you're looking with the polyprotic acid and you have to do a calculation. Because what you want to remember, just like when we were looking at the mixtures of weak acids previously, when we're looking at a polyprotic acid solution, the Ka value that's larger is going to dominate in terms of the pH of the solution. So even though it has two ionizable hydrogens, the Ka value of this first hydrogen is going to be the one that determines the pH of the solution. So this is the one that we have to calculate for. All right. As a reminder, when you have, let's look at different types of acids. Say that we have H, we'll leave this one here because we already have it. Say we have HC2H3O2, and then we have our ascorbic acid here, and then we have something like H3PO4. Okay. Acetic acid can donate 1 proton. Okay, if it can donate 1 proton, that's called being a monoprotic acid. Ascorbic acid can donate 2 protons, and it has them right out front for you to find. Okay, if it can donate 2 protons, it's called polyprotic. A polyprotic, or no, sorry, it is a polyprotic, but it's not specifically called that. It's called a diprotic acid. Sorry, I got ahead of myself. Phosphoric acid has 3 protons out front. So we're going to call that a triprotic acid. Now, any acid, and this includes our diprotic and our triprotic acids, any acid that has more than 1 hydrogen out front, these are called polyprotic acids. Okay, because they have like many protons, right? So it's more than 1 protons. And when you have polyprotic acids, you have to look at the Ka values to figure out which ionization, like which hydrogen ionization is going to contribute the most hydrogen ions to the solution, because that's going to affect the overall pH more. Okay, so in the case that we're looking at here, our first Ka value is like significantly larger than our second Ka value. So that's going to affect the overall pH of this solution. So we can really focus in on that in terms of finding the pH. Okay, so if we look at, we'll call it H2, C6, H6, O6 plus H2O. You know, we want to write out our formula just like we've been doing, okay? All of this is going to be the same. This first hydrogen is going to be the one that comes over here and attaches itself to the water, forming H3O plus. And it's going to leave the rest of the ascorbic acid behind. So what's going to be left behind is going to be H, C6, H6, O6, and the extra electrons with the proton left behind. Okay. From here, we're just treating this like a regular weak acid calculation. The real key here is going to be making that determination that the first Ka value is the one that we're going to hone in on in terms of finding the pH. Okay. You notice how we're back to having H3O plus as a product, and that's how we know we're going to be using a Ka value to solve for this. Okay, so we were told that we had 0.1 molar ascorbic acid, so our initial amount is going to be 0.1. Okay, and we're going to use Ka1 because it's larger. okay? We're going to set up our Ka expression using Ka1. So Ka1 is 8.0 times 10 to the negative 5 equals x times x divided by 0.100 minus x. We'll assume that this x value that we're subtracting is small enough that we can cancel it out of our calculation, and we'll check later. We'll multiply both sides by 0.100. And then we'll take the square root. Okay, we have 2.83 times 10 to the negative 3. It's going to equal our x value. And this will hopefully equal our H3O plus concentration. Okay, but we will check it out a little bit down here. So we'll do our 5% calculation. So that's going to be 2.83 times 10 to the negative 3. We'll divide it by our initial concentration of 0.1 molar, right? So we'll get that from over here. Multiply it by 100. And we get a percent of 2.83, which checks out. Okay, so that's great. That means that we can use this as our hydrogen ion concentration, and it means that we can calculate the pH directly from this value. Okay, so pH is going to be the negative log of our H3O plus. So the negative log of 2.83 times 10 to the negative 3. So our pH is going to equal 2.55. Okay, so there is your overview of all of the, or at least a bunch of the Chapter 17 problems. Okay, as always, let us know if you have any questions about anything, and keep on studying.